Welcome back to Beyond the Patterns. Today I have the great pleasure to announce Professor Dr. Daniel Cremers from TU Munich. So he is a very well-known scientist in the field of computer vision and machine intelligence. And if you don't know him, just let me shortly introduce him. So he received his PhD in computer science in 2002 from the University of Mannheim, Germany. Then he spent 2 years as a postdoctoral researcher at the University of California at Los Angeles, and 1 year as a permanent researcher at Siemens Corporate Research in Princeton. From 2005 until 2009, he was associate professor at the University of Bonn. Since 2009, he holds the chair of computer vision and artificial intelligence at the Technical University of Munich. His publications received numerous awards, including the Best Paper of the Year 2003, award from the International Pattern Recognition Society, the Olympus Award 2004 from the German Society for Pattern Recognition, and the 2005 UCLA Chancellor's Award for Postdoctoral Research. For pioneering research, he received 5 grants from the European Research Council, including a starting grant, a Consolidator Grant, and an advanced grant. In 2018, he organized the largest ever European conference on computer vision in Munich. He is a member of the Bavarian Academy of Sciences and Humanities. In December 2010, he was listed among Germany's top 40 researchers below 40. And on March 1st, 2016, he received the Gottfried Wilhelm Leibniz Award, the biggest award in German academia. He is also a co-founder of several companies, most recently the high-tech startup Artisense. So it's a great pleasure to welcome Professor Cremers here, and I'm very much looking forward to his presentation, and it's entitled Deep Direct VisualSLAM. Daniel, glad to have you here, and the stage is yours.
Thank you, Andreas. It's a great pleasure to be here. It's a great pleasure to be part of the series and to give a glimpse into our research. Yes, my name is Daniel Cremers. You introduced me nicely, so there's nothing more I can add, except that the work that I'm presenting today has been done largely by some current and former PhD students of mine, in particular Nan Yang, Lukas von Stumberg, Roy Wang, Jacob Engel, and Martin Oswald. Maybe a bit of background information about what we do in Munich. I hope you can see the slides. Yes, I'm heading the chair of computer vision and artificial intelligence at TU Munich, in particular running the computer vision group. We have at this point about some 30 employees, mostly PhD students and some postdocs. And we work on quite a range of topics in the field of computer vision, machine learning, robotics, and related areas. And it's a little bit, not enough time really to go into all the different topics that we're working on. And so I'm going to give you a glimpse into one specific area today. Beyond running my own team, I'm also involved in a lot of activities. Some of you may know that TU Munich is very much restructuring itself. For some reason, TU Munich is continuously restructuring itself. And here again, we are now changing to a system where the departments are merged into schools, larger schools. So there are going to be a number of schools that combine departments such as informatics, mathematics, and electrical engineering into one big school. And in addition, crossing these schools, there are so-called integrated research centers, I think 7 of them at this point. Two of them I'm involved in. One is the Munich School of Robotics and Machine Intelligence, short MSRM, and another integrated research center is the Munich Data Science Institute, where I'm one of the directors. Maybe a bit more about these integrated research centers. The idea is really that they try to bundle expertise in a certain area across different departments or schools. For example, the MSRM is very much focused on robotics and artificial embodied intelligence. So artificial intelligence, robotics perception, and there are quite a range of societally relevant application areas, including health, work, mobility, and also in the future environment. The Munich Data Science Institute instead is focused more on core machine learning and data analysis. So not just the foundations of data science, machine learning, but also domain-specific research in quite a range of different domains. So to give you examples, domains like natural sciences, life science, medicine, engineering sciences, social sciences, and economics. These are all areas that play a gigantic role for our society, where where machine learning and artificial intelligence plays an increasingly important role. And so we're trying to support this transition of algorithms and techniques developed in the field of machine learning to a broad range of application areas. These are TUM-wide structures. I'm also involved in national and European initiatives. For example, I'm one of the directors of one of the German competence centers in artificial intelligence called the Munich Center for Machine Learning, a BMBF-funded center. And I'm one of the directors of ELIS Munich. ELIS is the European Lab for Learning and Intelligent Systems, a decentralized lab that kind of brings together machine learning experts all across Europe. Yeah, so it's a lot of political activities, but today I really want to spend the rest of the talk on science and research, and I want to give you a glimpse a little bit into one area of research that we've been focused on. But let me start with an application where this plays a role, and this is the application that everyone knows, the challenge of autonomous driving, or what is usually called advanced driver assistance. We started in this field around 2005 in collaborations with Daimler. Here you can see they make sure that their logo is always in the videos that they capture. So what we did is we put two cameras in the car to film the action in front of the car. And the aim is obviously to help understand what's happening. Here is one output of so-called scene flow algorithms that we developed back 2008, where we can reconstruct the 3D structure of things in front of the car and color-coded here the motion of things in 3D. Here red means moving and green means stationary with respect to the world. So we can actually remove even the ego motion of the car. And this information is vital to understand what happens in front of the car, because motion in particular allows you to make prediction about what's going to happen next, right? And obviously, the further you can predict into the future, the more you can save lives and avoid accidents. So you can say if that same person keeps going with the same velocity, it will be in the driving corridor, say in the next 2 or 3 seconds. This is already a little bit old, but I'll come back to autonomous driving during my talk. Another field of applications that we worked on in robotics is the field of autonomous flying robots, or quadrotors. We started this around 2007 back in Bonn. Here's a picture of our first drone, a kind of a self-assembled drone. At the time, you could not buy them commercially, but then in the years after, commercial drones started to appear, powered by the TUM startup Ascending Technologies, and this is Crazy Fleet. You can see there's drones that are small enough to fit in the palm of your hand. So this is all nice, and it offers a great test bed for real-time computer vision. What we asked ourselves is, can we equip these systems with cameras, or one camera, and can we leverage computer vision, 3D computer vision, to do autonomous navigation? Some of them have cameras, but the little nanocopter on the right did not come with a camera, so we had to actually do 3D prints of camera holes and put cameras on them to make them fly autonomously. Here's just one result from back in 2012, where you can see we can program a drone to autonomously fire off some predefined pattern, as you can see here, right? And it uses the camera bottom right, and it creates a 3D map of the world in real time to localize itself. And then you can do many different demos. This is Jacob Engel, the person who actually did most of this work, who developed this as part of his master's thesis back then. Here the demo just shows that you can make it hover in a single spot in space, much like a little dog. It's always going to come back to the spot where it's supposed to stay. And this is a good test bed because it's a challenging problem of computing in real time and robustly the exact position in space. Robustly meaning even if you perturb the system by moving it away, by covering the camera, etc., does it still find its way back home? And there's more, but I'm not going to go more into the drones because I want to focus more on this challenge of 3D reconstruction from cameras. One of the classical problems in computer vision, and once it's combined with estimating the motion of the camera, it's sometimes called visual simultaneous localization and mapping, VisualSLAM, or also called structure from motion. And what I'm going to go into in the end of my talk, and this is part of the title Deep Direct VisualSLAM, is how we can leverage the predictive power of deep networks to boost the precision and robustness of these SLAM systems. But let's start from the beginning. Let's start with a calibrated camera setup where we have, say, a set of cameras that are calibrated so we know how they face the world. And all we care about is reconstructing the 3D world. We have these images, so this is a challenge that you all know from everyday life because you walk around this world, you see it with your eyes, but what you see are really only 2D projections of the 3D world. And one of the classical challenges in computer vision is how can I reconstruct the 3D world from these images? Before I go into how we do this, let's be more specific what we mean by 3D reconstruction, because honestly, there's a lot of different concepts what people refer to when they say 3D reconstruction. If we really, as in this project, want to have a dense reconstruction, how can we formalize this in the first place? We can take the world, a virtual kind of model of the 3D space, and chop it up into lots of little volume elements, often called voxels. And then for each voxel, the question boils down to saying, is that voxel part of the object or part of the background, right? So the voxel bottom left here has two possible configurations. It can be either object or background. That seems easy, right? Except if you consider two voxels at the same time, then each voxel can be object or background, right? So that gives you actually four possible combinations, right? Object, object, background, background, object, background, background, object, right? And obviously, with each additional voxel that I consider, the number of conceivable configurations doubles. With 3 voxels, we already have 8 possible foreground, background configurations. And with large n voxels, we easily see that the number of conceivable configurations or reconstructions on that lattice is 2 to the power of n. Now, I guess most of you are in computer science, so you'll know that's not good. It means exponentially growing search space. It means if I really try every single combination to see which one matches the images best, then I will never finish. Right? For those who are not in computer science, we can even detail it a little bit more. Let's say you take a volume resolution of 512 cube. That's not big, that's enough for Beethoven here, but if you wanted to reconstruct all of Munich, then this would be not enough for sure, right? So that's a fairly small resolution grid, and still on that resolution, we get 10 to the 40 million possible reconstructions. And now if I want to find an optimal reconstruction, what I really want is I want the computer to tell me among these 10 to the 40 million configurations, which one explains the images best. in whatever way you measure how it explains the images. What I want to get at is that the search space of conceivable solutions is prohibitively large. We cannot try every configuration to see which one is best. Right? Even if you take 1 nanosecond to evaluate one configuration, that's pretty competitive, still you would wait more than the age of the universe to actually get the best solution here if you tried every of them. Right? It means we have, if we want optimal reconstructions, we have to tackle the problem in a smarter way. Now, how do we tackle that problem of reconstruction? How do we measure how well a 3D model fits the images? Typically, you would do reconstruction by what's called triangulation. You identify corresponding points in 2 images, and given the known camera parameters, you can extrapolate the points along the rays of the through the pixels, so the camera centers, and where they intersect, you get your 3D location. That's all nice, except you don't have the point correspondence. And estimating point correspondence between pairs of images is basically one of the nastiest problems in computer vision. So the question is, can we tackle it from the opposite vantage point? And it turns out we can. We can go into 3D space and say, if that voxel here marked in green, if that voxel is on the object surface, and we assume it's visible and the object is Lambertian, then we should be seeing the same color in both images once we project the voxel into pairs of images. So we can basically check for color consistency, and using that color consistency or photo consistency, we can assign to each voxel a photo consistency. Because for points that are on the surface, we should see the same color. For points that are not on the surface, say out in space or inside the object, we don't typically see the same color because we're not actually looking at the same structure. Right? So with that reasoning, we can assign to each point in 3D space a value of this so-called photo consistency or color consistency, say in some interval 0 to 1, and by convention we'll assign small values near 0 for points like the green one where the colors match, and large values near 1 for points like the red one where the colors do not match. And with that, we can now go ahead and phrase reconstruction as an optimization problem. We can assign a cost function to any possible surface where we simply aggregate this photo consistency across all points of the surface, right? We integrate this row along all points of the surface, saying we want a surface S such that all points are maximally photo consistent in the sense of having a small value of rho. This is nice, it's easy. That way, in principle, from an optimization point of view, or from let's say, modeling the problem, you're done, right? Cost function, now compute the minimum. The challenge, though, is that, as I said before, the space of conceivable reconstructions, conceivable surfaces, is prohibitively large. So we can't just go ahead and measure that cost for every configuration and see what gives us the lowest cost. Traditionally, and most of you know this, the way this is optimized, much like you would nowadays optimize a deep network, is by gradient descent, right? But as you know well, once you have cost functions that are not convex, incidentally, typically deep learning cost functions are also not convex, you cannot guarantee that your solution is optimal. You minimize the loss, but it will get stuck in the nearest local minimum. And this holds here as well. A local gradient descent optimization in the space of surfaces would not work because it would get stuck in a local minimum. Now it turns out, and this was a breakthrough in 3D reconstruction, in 2009, we were able to prove that we can actually, for this class of cost functions, compute provably optimal solutions efficiently using convex relaxation techniques. The idea being that you replace this original cost function by an equivalent but convex one. Equivalent in the sense that there is a way to map the minimizer of the convex problem to the global minimizer of the original problem. I don't want to go too much into technicalities. This would be a whole separate talk of how exactly these convex relaxation methods work. But to say one thing, this is essentially what I was given this Leibniz Award for this work in convex relaxations for many problems in computer vision, because it gives you a way to compute optimal solutions where previous methods only found locally optimal solutions. So here's an example. We take a set of images, typically 20 or 30 images, calibrated images, so we know where the cameras are. And then we compute the photo consistencies, and then we can initialize, not appropriately like you would in a gradient descent fashion, you know, and if you look into deep learning, you know, the initialization of deep learning algorithms seems to be an art for itself, because you need to initialize appropriately and find appropriate parameters for this gradient descent for it to actually converge to a good solution. Here, we can initialize randomly because the algorithm is guaranteed to find a provably optimal solution. Like we can start with a block, and then the algorithm carves out the optimum efficiently. Efficiently means you don't have to try all 10 to the 40 million configurations to know that this is the optimum. It doesn't mean it's the best cost function. It means the best solution, but it is the best solution for the cost function that we set up. Meaning if you want better solutions, you just have to refine the cost function, the way you compute photo consistency, etc. But for that cost function, this is actually the global minimum. Turns out you can do more. Like if you, with cameras, you know, there's many advantages of doing 3D reconstruction with cameras. Traditionally, people would say, oh, if I want to get the best 3D model, why don't I take a laser scanner? And in autonomous driving, as you know, LiDARs and laser-based 3D sensing is still the standard, let's say, especially in industry. But I think what I'm going to advocate in this talk is that there are many reasons why you should move from LiDAR-based 3D sensing to camera-based algorithms. And one is the following: we can reconstruct actions in time using synchronized cameras, right? We can film this action, and this is footage that was obtained at the INRIA in Grenoble in Edmond Boyer's lab. Back then they had this camera system of 16 synchronized cameras. Now they bumped it up to 64. But here from 16 synchronized cameras, you see we can get reconstructions of an action at a level of precision where the entire rope of the rope jumping girl is reconstructed. So that's how accurate our 3D reconstructions already are. And using cameras, we can actually do it in time. This is something you could never do with a laser scanner. Now comes the next challenge. We have found ways to reconstruct from known camera locations. What if we don't know the camera location? Maybe because we don't have a way to calibrate it because someone took the photos and we don't know where they were when they took the photo. Or maybe because the camera is installed on a machine, on a robot, on a driving or flying robot, and at any given time, it can be anywhere, right? At that point, I need to solve a chicken and egg problem that goes very far back in the history of science, at least for computer vision. This is one of the oldest kind of references that you can cite. It's a paper from 1913, so a work that is more than 100 years ago by an Austrian mathematician by the name of Erwin Kruppe, who showed back then, more than 100 years ago, that once we have 5 corresponding point pairs observed in 2 images, we can reconstruct not just the 3D location of these points, but also the relative motion of the camera, up to scale, of course. This was one of, in a line of works that people worked on back more than 100 years ago. I find this quite intriguing because these are results that were obtained well before the advent of computers, right? So you might ask, what were they doing if they didn't even have computers to compute things? They did this manually, right? They had aerial images and they wanted, and then they were manually marked correspondences. Here's the point of the church tower in this image. Here's the point of the church tower in the other photograph. And then from a set of 5 corresponding points, they found the reconstruction. And it wasn't until, let's say, the 70s and 80s that people started to reproduce these results in computers. And the first real-time capable methods for this problem called structure from motion appeared around 2000 in Stefano Soato's lab at UCLA. When I joined them as a postdoc in 2002, the old 2000 demo was still running, and it actually did work in real time. So since then, there's been a lot of work in this. This is just a few selected works that had quite some impact in this field of real-time visual SLAM, as it's nowadays often called. A lot of these are very much inspired by Krupa's work in the sense that they take two images, they extract points, and then Krupa says we need corresponding points, so they go ahead and compute descriptors so that they can associate points and hopefully find corresponding points based on descriptor similarity of SIFT, SURF, brief, or some deep learning descriptors. This works fairly well, and it was developed over, one could say, decades to a framework that is fairly powerful. But I think there is a number of downsides. And I think primarily Krupa was a pioneer, but he was also misleading to modern computer vision. Why? Because when I switch on a camera, I don't see points, I see colors, right? And it's not clear how to associate brightness values or colors with points. Which points should I select in the first place? Which points can I drop? And once I drop all these remaining points, don't I lose potentially valuable information? Obviously, I do, right? And it's pretty obvious if you do statistical data analysis, you will know that you can, like using some Bayesian inference approach, you can only get the best solution given the data if you really consider all data and not just a small pre-computed subset of points. But next, even the correspondence is hard to compute. What if you make a mistake in correspondence estimation? That propagates into your solution and you can typically not recover. Or you have to go back to resampling correspondences using, using ransack and all sorts of heuristic strategies. It's a pretty nasty business, to be honest. Lots of heuristics are involved here. And in the end, you get solutions. They are good, but typically, you cannot guarantee anything. And so what we've been advocating over the last decade or so are so-called direct methods, methods that directly tap into the sensory information, the brightness values of your camera stream, in order to compute what you are interested in, namely the camera motion and the 3D structure. And intuitively, the idea is as follows. You say, find a 3D world with a color and a camera motion such that if I project this color from image 1 into the world and out into the subsequent images, I should have color consistency. So in other words, the key difference between these key point-based techniques and the direct methods, and often people say, what's the difference? There's points here, points there. Can you tell us what the difference is? Yes. The key difference is what is the loss function that drives everything? What is the loss function from which you compute camera motion and 3D structure? In the key point-based techniques, it's a bundle adjustment type loss function where you basically minimize a geometric reprojection error. The point distances in the image are being minimized. In the direct methods, instead, you minimize a photometric loss function. Color consistency is what drives all the estimations. To make that more concrete, here's one of our first breakthroughs in this line of research, a technique that we called LSD SLAM, for large-scale direct monocular SLAM. It's a somewhat involved approach, but it starts on the top left with an input video streaming in at 30 frames. And then there's two alternating approaches, alternating steps that track the camera and that estimate keyframe-based depths. And these depths are then merged into a point cloud. Now the camera tracking, let's look into that. I said what drives everything is color consistency. Here it is. The idea is that for all pixels X in the image plane, you have a keyframe image, I keyframe, and then you have the current image. You want to align the current image to the keyframe by what? By imposing that the colors, the brightness values I should be the same for every pixel. And you can see how I get from one camera to the other. I scale the point X in homogeneous coordinates by the inverse steps U. And then I rotate and translate with this rigid body motion G psi, 6 parameters, rotation translation of my camera. And then there's a perspective back projection pi that brings me back into the image plane. And so you really try to warp the images with a rigid body motion such that the colors match. And since you only estimate 6 parameters, this is easily done in a coarse-to-fine optimization strategy. And here you see how we can align and warp the structures to get a sharp alignment. And here's the whole system in action. It works on a single camera on a laptop CPU here in real time. You see the cameras being tracked, and as you see on the big screen here in the video, we generate reconstructions of this kind in real time and the trajectories of the camera while you walk around the world. And to my knowledge, it was the first large-scale capable real-time monocular SLAM system. Large-scale capable, you'll see in a second more videos, but we can reconstruct not just a table or a desktop environment, but fairly large indoor and outdoor environments from just one single moving camera. And the key challenge is to assure real-time performance, but also to assure sufficient precision that you don't see any significant drift in your reconstructions, any distortions. Because if you track a camera over hundreds of frames, and there is always a risk that you might drift. We'll see more examples here. This is the follow-up work, a technique that we call direct sparse odometry. The key difference is, there's many differences, but the key difference is here, note, top left is the input video, again, single camera. You see there's people moving through the scene, and in real time, we can reconstruct the camera trajectory and the 3D world represented as a semi-dense point cloud. The key difference to the LSD SLAM approach is that we jointly estimate a 3D motion, a camera motion and 3D structure. So not in an alternating fashion as in the LSD SLAM, but really in one single optimization using a Gauss-Newton type update step. And the way we get it to real time is that we don't estimate, we estimate the camera motion only for a set of a small window in time of keyframes, typically 7 or 8 keyframes, where we estimate the camera motion simultaneously. And this you see in these videos, once the camera keeps moving, there's a set of blue frames that are being jointly estimated all the time. And that gives us a certain consistency in time, but it allows us to do everything in real time. How do you evaluate the performance? You saw that we could go through a whole subway system and come back out the other side and have almost no drift. Almost no drift means there was, I didn't point it out, but there was a drift of about 2 or 3 meters. The bicycle was reconstructed twice in the end, the same bicycle, right? So we have a drift of 2 or 3 meters on a distance of hundreds of meters of walking. So it seems the drift is small, but how do we quantify it? And this is one of the biggest challenges these days, especially in the deep learning age. How do we quantify performance? How do we get ground truth for real data? And this is difficult here. Why? Because if we move around with the camera, we don't know where the camera was at any given time. Of course, in a room, we can install a mocap system, right, and track the camera ground truth. And then we can evaluate performance, but then we know the performance in that little room, right? We want the system to have good performance outdoor, in the subway station, on the road, in the car. We cannot equip the whole town with a mocap environment. This is just not scalable. It's not doable. Then we can go ahead and say, well, let's do a synthetic data set. Very popular, but I can tell you it's a bad idea in SLAM. Why? Because no matter how photorealistic your images are, if the method works on the synthetic data, it's not guaranteed to have the same performance in the real world. There is a gap between the simulated world and the real world, and it's not obvious how to bridge that gap. And photorealism is just one aspect. Just because it looks real to the human eye doesn't mean it's real. So what did we do? We recorded, as you could see here, lots of videos, real-world videos in many different environments with many different lenses. They are all very different, but they share one thing. They all have one thing in common. In each video, we basically loop back to the starting point. Like in the subway, we go through the subway, we come back out the other side, which means that we have a way to align the last image of the video to the first one. And as a result, we may not know where the camera was halfway through the video, but we do know where it should be in the very end. And so we can compute for every of these sequences a measure that measures the total drift in translation, rotation, and scale drift. And so we figured if you have enough sequences, and for each sequences you have numbers that measure the total drift per sequence, then that should give you a statistically reliable estimate of performance. And so here's the comparison to what's considered, or what was considered, the state of the art in real-time VisualSLAM, a very powerful key point-based technique called OrbSLAM from a team in Zaragoza. A very popular technique to date still. And what we plot here on the x-axis of these plots is the error in translation, rotation, and scale drift. And on the y-axis, we plot the number of sequences where we achieved a certain error. And now you want to maximize precision and robustness. So ideally, you want to end up in the top left. For as many sequences as possible, you want to have as small an error as possible. There's many ways, and then the dashed line is always real-time performance. This was 2016, I guess, these experiments are 17. So nowadays things would be faster, but back then this was feasible. In real time, if you had a bit more compute, you could get slightly more accurate. You can read these plots in many ways. For example, you can say, what is the best performance what is the error on the best 300 sequences? What error can I achieve? Maximum error on the best 300 sequences. OrbSLAM has an error of 6. We have an error of 1 approximately, which means the error was reduced by almost an order of magnitude. This is very important because in the deep learning age, people, they run their deep networks for classification on ImageNet. And typically, if you can get 0.5% better than the state of the art, you can publish a paper. Even if you're 0.5% worse than the state of the art, you can publish a paper. Here, we're not talking about 0.5% improvement. We're talking about almost an order of magnitude improvement over the state of the art. And similarly, if you want to measure robustness, because you want your method to really work in as many cases as possible, if we say we want a maximum error of 2, how many sequences from the 500 can we track with that error? OrbSLAM can track 100 out of 500. We can track 400 out of 500 with that error. So it's a dramatic increase also in robustness, if you will. Where does these improvements come from? Often people ask, how is that possible to get such a significant improvement in precision and robustness? In my view, it comes from the fact, as I argued, that we directly leverage the brightness values of the sensor to get these estimates. And we show that the more accurately you can model the sensory information, the more accurately you can model how the brightnesses come about in the camera from observing the world, the more accurate you get. So at that point, I figured, well, if you can track a camera at that level of precision in real time, completely unprecedented in terms of precision and robustness, there should be a way to make use of this for society, for example, for autonomous cars, machines, etc. But one of the challenges is it's always one thing to demonstrate performance in a research kind of gray code. But to actually bring this to the real world is typically a big gap. And there are so many wonderful technologies that are being developed in the research community that never make it to the light of the world, that never actually get into the markets, right? And so I figured, how can we support that transition into the market? And so we created a startup. These numbers, I just realized, are totally outdated. It's a startup, Artisense. I think in the end, we raised roughly more like 7 million or more in terms of investor money to support building a team in Munich. So it's a fairly sizable team. At some point, we were almost 50 talents. Now we're a little bit compressed again. I think at this point, it's maybe more like 25 employees. Artisense develops two things. One, Artisense develops sensory systems that include, in particular, stereo cameras, inertial sensors, and RTK GPS. And it synchronizes them, calibrates them, timestamps them properly, because all of this is very important for performance. And secondly, Artisense develops spatial AI algorithms that process this sensory data that build up on what I've just shown, but bring these technologies to a real time and to a robust performance in the real world. We have big cars where we demo our systems on real cars, but we also have toy cars that we can use for experiments and smaller demos. What has Artisense developed? So first of all, this is ICCV 2017. This is stereo DSO. So this is an extension of this direct sparse odometry to two cameras. And the use of two cameras has two benefits. One, with the baseline known between the two cameras, I can actually estimate the scale of the world. With one camera, you typically don't get the scale. Here we get the scale. But secondly, we demonstrated that having a second camera gives you additional precision. So you can not only walk through the subway, but you can actually drive through entire towns, as you can see here, and map the world at very large scale in real time and at high degree of precision. And this is important, for autonomous driving, having maps is vital. There's companies like HERE that made a big success out of mapping, except a lot of these maps are not computed in real time. They're computed offline, but as you know, the world we live in is a dynamic world. Objects can move around, so for obstacle avoidance, there's no purpose in having a map if it's a day old, right? These technologies instead allow you to create such 3D maps with simple camera-based sensors in real time. So we don't need expensive LiDARs. We can use cheap cameras to get 3D sensing. Now, to the part that I wanted to, that I mentioned in the beginning. As you know, computer vision since 2012 has been revolutionized by deep networks, and I'm sure that most of you are working on deep learning these days, a very popular topic. Interestingly, in the field of in the field of 3D reconstruction and SLAM, deep networks took a long time to catch on. So for example, for VisualSLAM, only around 2017, people started publishing deep learning-based approaches to this problem. It's notoriously a difficult problem, and I don't know why, but a lot of these early works did not achieve state-of-the-art performance. So most of the papers are more in the spirit of, yes, we can do VisualSLAM with deep networks, but if you want, state-of-the-art performance, you should rather use the existing, more classical optimization-based techniques. I think the reason for this lack of state-of-the-art performance of deep learning-based approaches was that often people try to tackle the problem in an end-to-end learning fashion. Say, in go the images, then a big deep network, and out comes the 3D world. And maybe that's just not feasible yet, or because the 3D world, it's so complex, and also the kinds of trajectories you can have and the kinds of 3D worlds, there's such a multitude that you can just not represent everything by sufficient training data. This is my belief why these approaches may not have been state of the art. So what we advocated over the last years are techniques that are hybrid, techniques that ideally combine the best of both worlds. And there is one field where deep networks really perform well. If you get just a single image, right, then classical SLAM methods can't do anything with it. If you don't have correspondence, at least with 2 or more images, what do you want to do, right? Well, it turns out if I showed you as a human this image and I asked you how far are the different structures, you could tell me, right? You could say that car in front of me, I don't know, maybe 7 meters, something like that. Of course, humans are never very good with numbers, but at least you have an estimate, right? So there's something that we know about the world we look at. And once humans can do it, obviously, we can also train a machine to learn that from images. And so there was 2017, a nice paper by Kuznetsov and collaborators who showed a deep network that, given a single image, could predict depths. It wasn't super precise, but it was pretty nice to see that, yes, it's doable. We built up on this network and we proposed a significantly improved network that we called StackNet. And you see it gives much sharper depth predictions here, for example. But beyond that, we can not only predict depths with the network, the next thing we did in this paper is we fed the depth prediction back into the SLAM approach. Basically using a classical SLAM method, like I mentioned them earlier, like DSO in particular, but then feeding a prediction of a deep network into it, saying, find a reconstruction such that it's most consistent with the depth prediction of the network. And this led to a technique that we call deep virtual stereo odometry. The name is often misleading. It's not a stereo method, it's a monocular method. The key idea, though, is that from just one image, we can predict the depths both for that image and for the right image if we had a right image. So we can, and the reason why we set it up in this way is that we can train this system without ground truth depths. All we need is a second camera. So in training, we run it with 2 cameras, and then we use the second camera for self-supervised training of the network, saying find the depths so that the colors are consistent with what I see in the training right images. But in the application, we only use 1 image. It's a monocular system. And then we can feed these predictions into the deep network, into the classical SLAM approach, and get a hybrid technique that gives us performance that is pretty much on par with what I showed earlier in terms of the stereo DSO. It's in fact slightly better than stereo DSO, except it only uses 1 of the 2 cameras. And so this was by far, and I think to date is still one of the top ranging monocular real-time capable systems. And here you see comparisons. This is the ground truth trajectory on Kitty. This is one of the Kitty data sets. On the left, you see monocular DSO, and you see it works, monocular DSO works nicely, except the scale drifts, right? You find the right structures, but always either shrunk or expanded, the scale tends to drift. Once you have 2 cameras with a known baseline, I mentioned this, the scale is not drifting, so you get a fairly good reconstruction. On the right, you see the deep network enhanced monocular system, and it seems to be on par, if not better. I'll show numbers in a second with the stereo DSO, which means I just said earlier that from a single camera, you can't get the scale of the world. And I taught this to generations of students in my multi-view geometry classes. And then turns out I was lying. You can get the scale from 1 single camera if you know the world you're looking at. Right? And deep networks, you can train them. And once they predict depths, it's absolute metric depths that they predict. And once you feed these predictions into the cost function as a regularizer, if you will, then the scale is being estimated along with the reconstruction. Here's numbers. So this is evaluations on the Kitty data set. The top sequences are the ones we tested on. The bottom are the ones we did not test on. And what you see is some of the top stereo methods: stereo LSD SLAM, stereo ARP SLAM, stereo DSO. The solid numbers are always the best performing number. And here comes the monocular method, DVSO. And as you can see, it's quite competitive. It seems to outperform the other methods, at least to a large extent. But in contrast to these stereo methods, this one only uses one of the two cameras, right? And so what we show here, and I'll come back to that message, the deep networks can be used to boost the performance of these SLAM systems in a way that they can compensate for missing sensory information. So rather than having two cameras, we can take one and a deep network. And we can extend that deep network prediction. For example, we just showed depth prediction. It turns out you can also predict the relative camera motion between consecutive frames, and you can predict with a deep network a notion of uncertainty. And then you can feed all these predictions into the SLAM approach. Here, more specifically, you can predict the relative camera motion if you have two consecutive images, and then you can again train in a self-supervised learning approach, saying, the residual is then the color consistency after aligning with the rigid body motion and after using the predicted depths and predicted camera motion. Now, if you do that for a real camera, brightness is typically not preserved. Typically, you have aperture changes that lead to affine brightness changes. So what can we do? Hey, no problem. We can predict the affine brightness change, right? So we can train a network given these two images to not only predict the depths and a camera motion, but also predict an affine brightness correction such that the two images after this affine correction coincide in terms of brightness values. So this is the same direct loss function that we used before, except now we use it for training the deep network. And this is what you get after correction. The images here are fairly well aligned in terms of their brightnesses. Now, if you take this out to the real world, you find for outdoor scenes like this one, there's a lot of structures in the world that are not Lambertian. Metallic structures on the cars, right? Or windows that are translucent where the brightness is not going to be preserved from one image to the next. What can we do here? Well, we can train a deep network to tell us what are the areas in the image where the brightness is likely not going to be preserved. And then we can simply take the self-supervised learning approach and downweight the residuals, downweight those areas in the image where the brightness is not preserved. And that works fairly well. Once you train a network, this is the prediction that you get. The bright yellow areas are the areas on the cars, in the windows, where the brightness is likely violated, or on the top right here in the moving trees, right? If trees move, then typically you don't have brightness consistency either. What's nice is, you see, we try to model the sensory information. That's the whole point I mentioned about direct methods, about understanding how the brightnesses vary from one image to the next. And what we do in deep direct SLAM now is that we use deep networks to help us model the brightness variations, right? It's not necessary that we as humans understand how the brightnesses vary. What's enough is that the deep network understands these variations. And then we use those as a loss function for SLAM. And once we do that, here's in evaluation. First, we evaluate the depth prediction, and we find we outperform existing methods, both classical methods, but also learning-based methods. Here, black is always the best, and blue is the second best. And what's nice is, even on untrained environments like the cityscapes dataset that we did not train on, the predictions of the depths and of the uncertainty here in the windows and on the cars is fairly consistent. So it generalizes quite well to unobserved environments. Next, we can evaluate the visual odometry. How accurately can we track the cameras here? A comparison to classical methods like stereo DSO and to OrbSLAM, but also to deep methods. On the KIDDI dataset, we get a dramatic improvement over the state of the art here as well. As you can see with this hybrid D3VO, we call it deep depths, deep pose, and deep uncertainty for VisualSLAM. And what's nice is, as I mentioned before, the use of deep networks allows us to compensate for missing sensory information. So here we compare to a monocular approach, DSO, a visual inertial approach where we enhance the camera with an inertial sensor, and a stereo inertial approach, state-of-the-art stereo inertial method called BASALT. And as you can see, the monocular approach, D3VO, is on par with the top stereo inertial method in terms of precision of tracking the camera. And so this again highlights the message that by using deep networks and leveraging this predictive power of the deep networks and fusing that into monocular systems, we can again compensate for a lot of sensory information and get a mono method that is on par with top stereo inertial. And as a result, here you see the reconstruction on the left with the mono method very blurred because the drift in the camera leads to basically a blurring of the reconstruction, whereas on the right you get a much crisper reconstruction because the trajectory is much more accurate. And then ultimately you can even go further and use the predictive power of deep networks to generate semantic 3D point clouds. This is a project we did in Berlin where we drove 8,000 kilometers of road, lots of streets in Berlin with a whole fleet of cars that was equipped with the Artisense sensory systems. And as you can see, we were able to map large environments, and we can distinguish the drivable area, the sidewalks, the cars, buildings, whatever your deep networks can predict. This is, I think, no groundbreaking result. It's very useful, obviously, but extracting semantic information from images is a classic, and obviously it's a no-brainer to color code the point clouds to get a 3D semantic world. But it's very important for autonomous driving because often you want to understand what is the structure I'm looking at. Is it a person? Is it a cyclist? Is it a car? Or is it just vegetation or buildings? That makes a difference in terms of avoiding obstacles, right? The very last thing I wanted to show, this is very recent, it's a work that's going to come up at CVPR this year. We can leverage deep networks to generate dense worlds. And this is from a single monocular camera. We can generate dense reconstructions of this type by a deep network that is trained to predict depths, right? Which I showed you we can predict depths. Now we can use multi-frame depth prediction and merge it into a dense reconstruction. One of the innovations in this particular work is that we can filter out moving objects. Once you don't filter out, you see what happens here. The objects get smeared out over, we'll see more examples. So this is actually an old video. This was before filtering out the objects. I didn't update the video yet. In the new one, the moving objects are essentially gone. But it's very useful because it allows you just from a single drive through the world, you can generate photorealistic, or at least fairly, here you see the smeared out moving object. You can generate fairly realistic 3D models of the world, dense colored models from just one single drive with the camera. And I think these kinds of 3D models could be used for training self-driving cars because they're virtual worlds, but they were generated from the real world. So they are ideally fairly faithful copies of the real world. Now to summarize, I'm getting to the end of my talk. I talked about our beginnings in autonomous driving in collaboration with Daimler, these scene flow approaches. I talked about direct VisualSLAM, how you can use directly the sensory raw data, the brightness values to generate camera trajectories and 3D worlds. Then I showed how to boost the performance of these direct SLAM methods with deep networks that help us understand how the brightness, what brightness variations we can expect, where brightness is likely preserved, where it's not preserved, etc. So we can use the deep networks to boost the performance here. And in particular, we can deploy it for autonomous systems, for large-scale mapping of the world. We get 3D maps. We get location information, very precise location information, even in the absence of GPS. And lastly, we can even generate semantic 3D reconstructions of the world at very large scale with very low-cost hardware. Thank you for your attention, and I'm open to questions.
Thank you very much for this wonderful presentation, and I have some applause for you, so I hope you can hear that.
Thank you. That's the first applause I ever got on a virtual.
Yeah, talk. So we try to compensate for the limitations that we have in these virtual sessions, but you can be sure that our entire audience would be clapping now for the wonderful presentation.
Thank you.
Really amazing work, amazing, and also wonderful the tour from, you know, the small scenes starting with and then expanding this to entire cityscapes being reconstructed with semantic information. I think this is quite amazing what has been achieved over the last few years. Actually, it's not so long. If you show that some results are from 15 years ago, I think.
Mm-hmm. Yeah. The things have moved dramatically fast in the last few years. Yeah.
That's I'm very impressed by the presentation.
Thank you.
So one question: when you reconstruct over time, do you also use a temporal consistency term for the regularization? So you had this example with the 24 cameras and then later 64.
Yeah.
Is that a common thing?
So yes and no. This is a very important challenge that I think is to a large extent still open. Do we use temporal consistency? In the time, this is 2014 ECCV, the rope jumping girl, there is some temporal consistency that we used, basically just a temporal smoothness assumption, right? But that is not very powerful as a regularizer. And in fact, if you think more about this problem, you come to realize that what you really want to do is you want to impose, you know, you say you have a rope jumping girl, and this is something that I think humans do. How do they regularize what they see? They have an understanding about the world they live in, right? They see the physics underlying the world. You know, and this is something that's been fascinating me for many years, since 2014. Can we model the physics in this scene? Can we model the fact that the rope is not just moving with constant velocity or something like that, but can we model the fact that whatever I should see should follow the Newtonian laws of motion? Because I know the world around me follows the Newtonian laws of motion. So if I can infer the forces between things, the elasticity of the rope and the momentum at all, and then bring in the constraints of physics, that should give me the most powerful regularization. Because then I could actually continue the rope jumping and simulate the whole phenomenon using physics. And it took us many years to do that, because you can imagine this is very challenging. You have to go deep into physical simulations of deformable objects. Well, it turns out just last year we did achieve a breakthrough here. And this was a paper at CVPR where we actually simulate the physics of things. And we fit basically a physical simulation of a deformable object to video data. Unfortunately, I don't have slides on this right now. It's a pity. It would take me too long to find the slides.
But for our viewers that see the recording, we can at least put the reference into the description of the video.
Yes.
That would be, and by the way, we'll also try to include all the other references that you've been showing, because our viewers are probably very interested in that.
Yes. So this is Sebastian Weiss et al. CVPR 2020. This is the reference that I'm referring to. I can actually try to find, maybe if you want to do another question in the meantime.
That after the recording, don't worry. There's another question here. So how do you deal with color? So you showed that intensity variations you can model, for example, with a deep learning approach from within one SIEM or one camera model. How more difficult is it to calibrate that across different cameras? So let's say if you have internet databases where tourists uploaded photos and so on, is that a much bigger challenge, or can it be tackled with similar approaches?
I think it can be tackled. These are typically different problems. And in fact, I always talk about SLAM as if it was one problem, but the truth is there's lots of variations of SLAM. And this is why I mentioned it earlier. When you say camera-based reconstruction, this is often apples and oranges. People do different things, different challenges. So, and in SLAM, even if it's about reconstructing the world and the camera motion, you typically distinguish this photo collection challenge. There's famous papers like Building Rome in a Day. Noah Snavely and others worked on this a lot. And this is often more, you have a small number of images, maybe 20 or 30 images, but often wide baseline. And then you typically work in an offline manner, typically not real time. Also, call map is an example, right? Of a fairly powerful technique that tackles that challenge. And then you have to distinguish that from online real-time driving camera, where the difference is you often are constrained by real-time performance requirements, but on the other hand, from frame to frame, you typically have small motion. And this is kind of the SLAM that I've been focused on, is this real-time incremental tracking of a camera. Even there, you want to get global consistency ultimately, and we've been trying to implement global consistency in these approaches as well. But it's typically still two different challenges today: the wide baseline, not real time, and the small baseline real-time approach.
I mean, the real-time constraints are, of course, also a huge challenge, because it's not so much time that you have to do the computations.
Exactly.
There's just a question whether I got that right. When you showed the improvements also of the depth map estimation, are you actually using the photometric consistency across the views as a regularizer or as a kind of multitask loss for this? Because I would assume that the reconstruction, you can also backpropagate a gradient through. So is that what you're basically doing?
We have this brightness consistency as a loss, and we backpropagate through it, yes. Yeah. That's what we do, yeah. I found the papers that I mentioned earlier about the question of physical simulation. If it's okay, I'm just going to share those.
Yeah, sure.
Which one is it? I think this one, yes. So what you see here is first synthetic data. Again, we start here, as often we start with synthetic data. What you see on the left in this video, is a dragon, not very pleasant because we kind of fix it at the neck, and then it oscillates. You see, it's an elastic, it's a classical graphics figure, and you see that because of the elastic parameters of the object being different, the initial simulation is inconsistent. Initially, it's the same, but with time, it drifts apart because it's more, the initial configuration is kind of more rigid, right? It has a different elasticity. And then what we do is we basically optimize the physical parameters of the initial object so as to best fit the observation data. And again, like in the direct methods, everything is driven directly by the sensory data. We say find elastic parameters of this deformable object such that it best fits the data. And this goes in the direction of inferring the physics and the elastic or physical parameters of objects from measurements.
And here you're operating on a mesh representation of the object, or is this also based on
it's a actually finite element simulation of the whole object. And that took us a lot of time to get this working because it's pretty involved. Here's then with real data, this is a teddy bear. So what we did here is we scanned the teddy bear first, and then we and then we have a finite element simulation of the teddy bear, assuming certain initial parameters of elasticity and Young's modulus, etc. And then we optimize these parameters so that it best matches the observations. And then you get out, this is the initial configuration. You see it's much more rigid. And here, this is after optimization. It's much more kind of softer and not as stiff as the initial one.
Amazing.
Yeah, I could watch this forever, but it's... I should stop the video. But this is quite challenging, I should say, because what remains open is, can you also infer the simulation parameters along with the shape? Can you generalize this to very complex scenes with a lot of interacting objects? And then if you have humans, they have a lot of internal forces. If I move like that, the teddy bear, once you drop it, it's a passive thing. It doesn't have muscles, right? But humans have muscles, so they actually create forces that change things. And inferring all of these parameters from observation, somehow humans do it. How humans do it, I don't know. But this has always fascinated me. How, for example, as a human, if I throw you a tennis ball, you can catch the tennis ball. Obviously takes practice. I found that as a kid that you need to practice a lot to be good at it. But once you practice a lot, at some point, you can even close your eyes and catch the tennis ball. If you see the beginning of the trajectory, just a fraction of a second, I can put my hand and catch it. And, 50% of the time it actually works, which means somehow my brain is able to predict the trajectory of the flying ball several, even maybe a few seconds or so into the future, all the way to the time of impact. Because if you don't know the time of impact, you will never catch the tennis ball, right? So how the humans do that, I don't know, but it's quite fascinating. And it's pretty clear that humans infer a lot of the physics of the world. You see a bouncing ball, you get a feeling of how heavy it is or how elastic or plastic it is. All of these things, we immediately infer them because we need to know the properties of the world. And somehow we can do that with our eyes. And I think this is, for me, one of the biggest challenges that my ERC Advanced Grant is focused on. How can I infer the physics of the world from images, from observations, from cameras?
It's quite amazing, and there you probably also need maybe priors in order to get the initialization done and so on.
Yeah.
Because that's probably also what humans do. And I mean, you immediately notice if the simulation is not accurate, that an object just does not behave as you would expect it to.
Yeah, exactly. And this is, in some sense, you can say a classical problem. There is inverse kinematics and all of that in graphics as well. But I think what needs to be revisited is typically first people from cameras reconstruct the shape for every time step, and then they fit the model to it. But I think what needs to be done is you need to fit the model directly to the observations. And this was our first attempt to do that in this CVPR paper last year.
Absolutely.
Maybe a short advertisement on that level. We are at this point desperately looking for researchers, in particular on the postdoctoral level, to support our activities. These kinds of challenges, this is not an easy challenge. It needs talented people to tackle it, and so we're very much looking for people.
Absolutely, and I guess that I can share that also in my network, and would be very glad to collaborate with such things in the future. Daniel, this was really an amazing presentation, amazing results, developments over the year up to estimating the physical properties of objects, and I think this at least deserves another round of applause. It deserves much more. But the round of applause is all that I can offer right now.
I understand. That's totally clear. Thank you so much. Thank you so much. It was a great pleasure, and hope to hear from people soon. If you have more questions later on, feel free to drop me an email or contact me.
Thank you very much for that offer, and thanks for visiting us. So you've seen we had a wonderful presentation, wonderful videos, wonderful results, a great overview on the state of the art in computer vision regarding SLAM. And you see that we also had a vivid discussion. But the discussion, of course, doesn't end here. As Professor Cremers already said, he would be very glad to answer your questions. So if you do have any questions, you can leave them here in the comments, or you can directly send them to us by email, and we'll be very glad to answer them. So I hope you enjoyed this video as much as I did, and I'm very much looking forward to seeing you in the next video. Bye bye.